Welcome to Semester 2 of Second Year Chemistry. The first section of CHEM2402, 2912 and 2916 is molecular thermodynamics, which will be followed by classical thermodynamics. The central question for molecular or statistical thermodynamics is, how do the properties of individual molecules give rise to macroscopic or bulk properties and behaviour of chemical systems? This means addressing big, general questions like what is temperature, what is heat, and why is there an absolute zero? Why are some processes spontaneous and others not? And what is equilibrium? Or why do equilibrium constant expressions look the way they do? So, what properties of individual molecules do we need to know about? We need to know about their quantum states. You already know from first year and CHEM2401 that electronic states, or orbitals of atoms and molecules, have discrete or quantized energies. Solving the Schrödinger equation for electrons confined by a potential energy always gives rise to discrete energy levels that correspond to atomic or molecular orbitals. So the Schrödinger equation, shown here, is used to calculate the wave function, as well as the allowed energy corresponding to each electronic quantum state associated with a particular quantum number. In CHEM2401, you've seen the Schrödinger equation solved for models like the particle in a box for the electronic states of conjugated molecules like butadiene, shown here. In CHEM2401, you also saw that vibrational states are quantized, and you've seen the Schrödinger equation solved for the harmonic oscillator model for vibrational wave functions and energy levels. This model, which we will also use, gives equally spaced allowed energies. Of course, vibrations of bonds can only occur in molecules and not in single atoms or atomic ions. You've also compared the harmonic and anharmonic oscillator models for vibrational energy levels and used these to understand vibrational spectroscopy. Whereas in harmonic oscillator energy levels are equally spaced, in real molecules or anharmonic oscillators, energy levels get closer together as energy increases, and near dissociation, the energy levels get so close together that they become almost continuous. Other kinds of motions, also known as degrees of freedom, are also quantized. In CHEM2401, you saw that vibrational spectra have rotational fine structure, although you did not examine it in detail. Vibrational or infrared transitions are not perfectly sharp due to the effect of discrete molecular rotational quantum states, shown in the circles here. This comes about because rotational motion is also quantized. Molecules may only exist with discrete amounts of rotational energy about each possible axis of rotation. Once again, atoms do not have rotational states. This is because their mass is concentrated in the nucleus, which is also their center of mass. The final kind of motion to consider is translation, which is also quantized into discrete states. An atom or molecule in a gas may also have a translational kinetic energy. As atoms or molecules are particles in a box, translational energy also occurs as discrete energy states, although for a big box, the states are very close together in energy. We'll actually recycle the particle in a box model used for delocalized electrons in CHEM2401 to describe the translational states of atoms and molecules next week. So the state of a molecule is just the amount of energy in each of its degrees of freedom. This is the same as knowing the quantum state of each of the electronic, vibrational, rotational, and translational degrees of freedom. For example, the state of a diatomic molecule is completely specified by its electronic configuration, vibrational quantum number, rotational quantum number, and translational quantum state. The total energy of that molecule is also just the sum of the energies of each degree of freedom. If we know this, then we have a complete description of that molecule. An atom or molecule is completely described by its molecular state. Our task for the first part of this unit of study is to extend this to describe a system of many molecules. To do this, we will simplify the maths and make an abstract model of a particle which has only one degree of freedom and therefore only one set of energy levels.